Last time we built an adder, it takes two numbers and adds them together. That's one operation, addition, check. But a real CPU needs to do much more. It needs subtraction. It needs logic operations like AND, OR, and XOR. That's a lot of operations. Do we build a separate circuit for each one? That would be wasteful. Turns out we can be clever. We can reuse what we already have. Let's start with subtraction. How do you subtract with an adder? Think about it. 5 minus 3 is the same as 5 plus negative 3. So if we can represent negative numbers, we can just add them. But how do we represent negative numbers in binary? There's an elegant system called 2's complement. To negate any number, you flip all the bits, then add 1. Let's see how that works with 3. 3 in binary is 0, 0, 1, 1. Flip all the bits, 1, 1, 0, 0. Add 1, which gives 1, 1, 0, 1. That's negative 3 in 2's complement. So the formula is a minus b equals a plus not b plus 1. Look what that means for our adder. We add NOT gates on the b inputs and then set carry in to 1. And we have just built a subtractor using our adder. Same circuit, slightly different inputs. Now we have add and subtract, but we still need to choose between them. Enter the multiplexer, or MUX for short. It has two data inputs, one select line and one output. When the select is 0, output equals the first input. When select is 1, output equals the second input. It's like a railway switch. The control signal decides which track connects to the output. We can build it from the logic gates such as the AND and the OR gates. First we AND each input with the select signal, then we OR the results. What if we need to choose between more than two inputs? We add more select lines to the multiplexer. One select line can be 0 or 1. That's two possibilities, two inputs. Two select lines can be 0, 0, 0, 1, 1, 0, or 1, 1. That's four possibilities, so we can choose between four inputs. This is called a 4-to-1 multiplexer. Now we can build the ALU, or the Arithmetic Logic Unit. It does multiple operations and control signals select which one. Here's the architecture. We compute multiple paths in parallel. One path for addition and subtraction, one path for AND, one for OR, one for XOR. All four operations compute simultaneously. Every time inputs arrive, all paths produce their results. Why do we do it this way? Because it's simpler. This way we don't need extra circuits to turn paths on and off. The paths are always running and the unused results just sit there. At the end, a multiplexer picks which result to send to the output. Think of it like TV channels. All channels broadcast at once. You just pick which one to watch. The selection is controlled by what we call an opcode. The opcode is just 2 bits that tell the ALU which operation to output. In this example, opcode of 0, 0 is for addition, 0, 1 for AND, 1, 0 for OR, and 1, 1 for XOR. Let's see it in action. A equals 5, B equals 3, with opcode 0, 0, which means we are adding A and B. Result, 8 or 1, 0, 0, 0 in binary. Now change the opcode to 0, 1 for the AND operation. This gives the result of 1. Same inputs, different operation, just by changing the control signals. The ALU gives us a result, but sometimes we need to know more than just the answer. Was the result 0? Was it negative? Did something go wrong? The ALU can answer these questions with what we call status flags. First, the 0 flag. It tells us, is the result exactly 0? To check, we just NOR all the output bits together. If they're all 0, the flag lights up. Next, the negative flag. Remember 2's complement? The leftmost bit tells us the sign. If that bit is 1, the number is negative, so we just read that bit directly. Finally, let's look at the overflow flag. Sometimes an operation produces a result too big for our bits to hold. This is done by the XOR of the carry-in and carry-out bits at the most significant bit. The overflow flag warns us when the result is too big for our bits. Why do we care about these flags? Because programs need to make decisions. Jump to a different instruction if the result was 0. Take a different path if it was negative. These tiny flags are how the CPU knows which way to go. Let's step back and see what we've built. We started with an adder for addition. Then we learned 2's complement, and our adder became a subtractor too. We added logic operations, AND or XOR, and we used a multiplexer to choose which result to output. The result is this: the Arithmetic Logic Unit. 2 inputs, 1 output, a handful of control signals, and it can do any operation we ask. But there's something these circuits can't do. They react to their inputs instantly. The moment the inputs change, the output changes. But what if we want to save a result? What if we need to remember something? Right now we can't. Next time we'll fix that. We'll build circuits that remember.